Hi everyone, and welcome to the first installment. I've provided you guys notes of all of the stuff I'm going to be talking about for this segment of the class. And on the very first page, at the very top of the page, I have this statement: "What is the question?" And that was a phrase that was actually drilled into my head when I was in graduate school. I was in a lab group that whenever we'd be tossing around ideas about experiments that we were thinking about doing, or things that we were interested in, there was always this barrage from everyone in there saying, "What's the question, Jim? What is the question?" And what I learned from that experience is that if you think really carefully about what your question is, life is a lot easier for you, scientifically at least. And what I do, and I still do this to this day, and I encourage all of you to do this, and I encourage everybody else that I interact with to do this, is to, as you start to develop ideas and you want to do some science on it, is to actually literally physically write down on a piece of paper what the question is. You learn a lot about your question by actually writing it down and sitting back and looking at it. You might realize that that question is way too big to answer in one lifetime. Maybe I should refine my question to make it something manageable. But the other thing that is really handy when you start writing down the question is then you can design an experiment that is explicitly aimed at answering that question. And I know that sounds obvious, but you would be surprised how often people collect a bunch of data, they do an experiment, and then they haven't really thought through how they're going to analyze those data, and they realize that, that experiment actually isn't addressing the question like I thought it was. And so if you actually write it down and you plan it out, you're much less likely to get into that horrible, horrible situation where you've done tons and tons of manual labor and spent hours upon hours in the field or in the lab, and then you're like, well, how am I going to analyze this data? And as somebody who does help out a lot of people, with their statistical analyses, oftentimes I'll talk to them if they're going to redo the experiment. It's like, if you had just done this one thing slightly differently, this whole problem that we're having would go away. By doing all of that work beforehand, hopefully you'll never find yourself in that situation. And so what we really want to do is we want to think carefully about what our question is, and then we can design an experiment around that question. And then hopefully what we've also done is we've thought really clearly about how we're going to analyze those data. The best situation to possibly be in, which I encourage all of you to try to be in at all times, is that when you collect that last datum, it should not take you long at all to analyze those data. In principle, it should take you maybe, I don't know, the minute it takes to boot up R. You've probably already written the code because you've thought about it beforehand, and you're done in a couple of minutes. And then you can just go ahead and you can interpret the results of those analyses and see what you learned, and maybe write up the study, or go on and do an additional experiment to confirm or whatever based upon the results of that first experiment. But again, the important thing here is that is the designing an experiment and thinking about how the analyses are going to work is really the challenging creative part. In my opinion, it's the fun part of science. Well, one of the fun parts. The other fun part is when you actually go out and collect the data. Like, I get to hike around in the Sierra Nevada, swinging a butterfly net and sleeping in a tent for a month and a half a year. And that's great, but you enjoy it that much more when you know exactly what you're going to do with the data that you collect, as opposed to always having this like haunting thought in the back of your head of, how in the heck am I going to analyze this? We never want to be there. And so with thinking about that, now we are going to be collecting data. I've been throwing around data. All data is it's just a collection of things that we can kind of assume are facts, that they are something that we've observed or measured that reflects a fact. If I weigh something and it weighs 10 grams, that is a fact that it is 10 grams. That's how I'm gonna approach that. And when we have a collection of all of that stuff, that constitutes data. And then once we have those data, now we can start thinking about how we're going to model them. And the first step with thinking about how we're going to model our data is to understand what type of data do we actually have. And there's a few different types of data that we want to consider. So one type of data are data like categorical data. And categorical data, as the name implies, are things where things can be dropped into various categories. And there's actually two different types of categorical data. There's what's called nominal categorical data, and this could be yes or no questions. This could be, was it living or dead? What bin does it go in the live bin or in the dead bin? It could be flower colors, purple, pink, and orange. Those are bins that we're putting things into. They are categories, and we're choosing to put the data into their appropriate category. The other type of categorical data is what's called ordinal data. And these types of data are data that are inherently ranked. So it could be small, medium, large. It could be, egg, juvenile, adult. I think the example I used in the notes was different insect stages. So it could be a first instar caterpillar. It could be a second instar, third, fourth, fifth. So these are ordered. Just like with small, medium, large, we know that small is smaller than medium, and medium is smaller than large, which means that small must be smaller than large, right? Whereas with just nominal categorical data, if we were thinking about flower colors, sure, everyone has their favorite color, but there's no inherent order in those data. And so if you're dealing with categorical data, you also want to think about, well, is it going to be nominal or is it going to be ordinal? Because there's going to be different statistical tools that you're going to want to use depending on what types of data those are. The second general type of data, and the type of data that we're going to primarily be dealing with in this course, is numeric data. And numeric data, as the name implies, is numeric. It's numbers. And there's two different important types of numeric data that we're going to want to consider. The first is continuous data. So continuous data are those data, as the name implies, that occur on a continuous scale. And so they can take on, in principle, any value between maybe some range or any value between negative infinity and positive infinity. But the important thing is they can take on any possible value. The interesting thing about continuous data that oftentimes people don't think about is that we can actually never know the true value. So even though we're going to think about data as being a collection of facts, all we can do, the best we can do with continuous data is to come up with an approximate value for it. And I know that might seem counterintuitive, but think about if you were weighing something. Let's say that we were going to weigh acorns. And I don't know why I'm picking acorns, but I'm assuming nobody has a problem with acorns. So let's say I was interested in knowing how much an acorn weighed, and I could stick it on a scale. Let's say I stick it on one of those cheaper scales that you can buy from Fisher Scientific for, $40. And I could get there, and maybe I can get how many milligrams that acorn is, but that's all I can get. And then I could spend a little bit more money on a more expensive one, and maybe I can get down to the 100th of a milligram. Or I could spend even more money on a more expensive scale, and I can get to 10,000th of a milligram. Well, in principle, you could just keep adding significant figures to that value. So you're going to get a more and more precise estimate of what that value is, but you can always add an extra significant figure to it. And clearly, there are no scales out there that have an infinite number of significant figures, but in principle, why not? Just because it's the limits of our technology. And so we can think about the accuracy at which we're measuring a continuous variable is going to be determined by the precision of the instrument that we choose to measure it with. And I often refer to this as grain. So you can have a coarse grained estimate where maybe you're just using a kitchen scale to measure the weight of an acorn, or you could go into somebody's lab here on campus and you could weigh that acorn on a $10,000 scale that'll give you, 10 significant figures as to how much that acorn weighs. And so that's just something to keep in mind, that the precision at which you're measuring something is going to really determine how close you are to the true value, but that you can actually really never know the true value. The second type of numeric data are what are called discrete data. And discrete data, as the name implies, are discrete. They are integers. Generally, we can think about things as like things that we can count. And so this could be like the number of offspring that a bird has, or maybe it's the number of lesions on a leaf if it's been infected by a pathogen, or the number of leaves on a plant if you're using that as some response variable that's telling you something about the performance of that plant. The point is that they're integers. And as I said, in this class, we're going to focus primarily on numeric data. And when you're collecting numeric data, it's really, really important to know right off the bat, okay, am I dealing with continuous or am I dealing with discrete? Because we're going to use different distributions to model discrete versus continuous data. Okay, more on that later as we start to develop and play around with models. One last thing that I wanted to mention, because it's a term I'll be throwing around a lot over the course of the semester, is this concept of a random variable. And so in a statistical mathematical framework, a random number or a random variable means maybe something a little different than it means in the common vernacular. And so in statistics, when we talk about random variables, we're explicitly talking about a situation where we do not know the value of something until we measure it. And I know that sounds pedantic, but as long as we can kind of get our heads around, okay, that's what the definition of a random variable is. I don't know the value of it until I see it. Concepts such as degrees of freedom will become much more intuitive as to why we're keeping track of degrees of freedom if we keep reminding ourselves that we are going to model these data that we collect as random variables. The other important thing when we're thinking about random variables is generally when we're going to describe a collection of random variables is we're going to make some kind of assumptions about what the underlying distribution is that we're sampling those from. And you can think of it as the shape of the population that we're taking random samples from. So for example, when we calculate the arithmetic mean of something, and we talk about like, oh, what's the average height of people, or whatever it might be, when we are deciding to take the mean of something, we are implicitly being very explicit about what we're doing. What we're actually doing is saying we are going to calculate the mean, assuming that all of our data are random variables drawn from a normal distribution. And there's lots of other continuous distributions out there that might be more appropriate. But if we decide that we're going to take the arithmetic mean, we're probably assuming that the underlying sampling distribution is a normal distribution, which could be right or could be wrong. That's why it's really important to think about how you're choosing to model your data. Another thing that I'll say a bunch probably over the course of this semester is the old adage that all models are wrong, some models are useful. And it's important to always remember that we're going to have to kind of idealize what we think where our data are coming from, and then we're going to model them based upon those assumptions. And actually with my example with the calculating the arithmetic mean of a sample, saying that we're being explicit that that they're random variables drawn from a normal distribution. Actually, more explicitly, when we're calculating the mean, what we're doing is saying, I am going to calculate the maximum likelihood estimate for the parameter mu, assuming that my data are random variables drawn from a normal distribution. And I know that sounds like a mouthful, and it sounds incredibly pedantic, and it is incredibly pedantic. You probably won't win a lot of friends by pointing out to them it's not really the average. What it is the maximum likelihood estimate of your data, assuming that they're random variables drawn from a normal distribution. So I'm not encouraging you to correct people, but I am encouraging you to always know that in the back of your mind, that's what we're doing when we are modeling data, is that we are going to make certain assumptions about the underlying sampling distribution. And once we have that underlying sampling distribution, then we can do statistics. Once we have the statistics, we can do statistical hypothesis testing if we want, and ask various questions of our data. And so I wanted to point out what random variables were because, as I said, I will use that term quite a bit over the course of this course. And so that's kind of our general introduction. And what I want to do now is we can go on and we can talk a little bit about some discrete random variables. Okay, let's think about the simplest discrete distribution that we can, and it's a distribution that's called the Bernoulli distribution. And a Bernoulli distribution is, again, it's going to be a discrete and it is going to be a number. And in this case, the number is going to either be 0 or 1. Okay, let's think about the simplest discrete distribution that we can, and it's a distribution that's called the Bernoulli distribution. And a Bernoulli distribution is, again, it's going to be a discrete and it is going to be a number. And in this case, the number is going to either be 0 or 1, okay? And so the Bernoulli distribution, it's the simplest one, is that there's only 2 possible outcomes. And so if you were thinking about flipping a coin, for example, there's 2 possible outcomes. You're either going to get heads or you're going to get tails. And then there's going to be a probability that you're either going to get heads or that you're going to get tails, okay? And so generally, that's written as, say, P equals 0.5. And so that, let's say, is the probability of getting heads. So every time I flip a coin, there's a 50% chance that I'm going to get heads. If I flip a coin just once, that is a Bernoulli random variable. I have made, I don't know the answer to whether it's heads or tails until after I have flipped the coin, and presumably I have some estimate as to the probability of getting heads or getting tails. So in this case, we have a lot of prior knowledge about how coin flipping works, and we feel pretty good that the probability of getting heads is 0.5. And so that means that the probability of getting the other outcome is going to be 1 minus P, which is going to equal 0.5. Okay. A lot of times in books, what you'll see is that this 1 minus P will be written as Q. Okay. So again, we can think about this as being, I don't remember what I said, the probability of getting tails, and that means that Q is the probability of getting heads. P plus Q will always equal 1. The probabilities, whenever we're dealing with anything with any kind of a distribution, the probability will always sum up to 1, meaning that we are accounting for all possible outcomes. There's a 100% chance that you're either going to get heads or tails. That's another way that you can think about it. And so let's play around a little bit and think about how to deal with these probabilities by taking a kind of a more interesting, I would argue, a more interesting example than a coin toss. And we're gonna think about this butterfly that is really close to my heart. It's one of my study systems. It's a butterfly called Lyciides melissa. It is, or the Melissa blue. And I have a picture of one just because they're so darn handsome. Everybody wants to see something handsome. Look at that guy. That's a handsome bug right there, isn't it? That's my bug. So this is the Melissa blue. Top side of the wings are this beautiful blue color. And they have colonized patches of alfalfa throughout the Great Basin out west. And based upon lots and lots of work, we know that the probability that if you go to any feral alfalfa patch in the middle of the stinking desert, that there's about a 32% chance, let's say that there is a 32% chance, that the Melissa blue butterfly will be present in any random patch. And so going back to this, we can go ahead and we can start with P is 0.32. And so, oh, that felt good. So if we know that P is 0.32, the probability that it's present, that means that the probability that it's absent has to be 1 minus P, which again, some people refer to as Q, okay? And that's going to be 0.68. And again, 0.68 plus 0.32 equals 1. All possible outcomes are now have been accounted for. And so we can start with kind of playing around with how this might behave by saying, let's assign P to be 0.32. Okay, so now we have this object called P, and it's worth 0.32, which means that we know what Q is. Q is going to be 1 minus P. And so now let's take a look at Q, 0.68. Turns out I did my arithmetic, it worked. Okay. So let's think a little bit about how we play with probability. So if I wanted to know the probability that that butterfly is present in any two random patches that I would go to in the field. So I randomly go to two different alfalfa patches, and I want to know what is the probability that it's present in both of those fields, assuming that the probability that it's in any given field is 0.32. And so to do that, we always multiply probabilities together. So it would be the probability of it being in the first, and then the probability that it's in the second. Okay, so I would expect roughly 10% of the time, if I went out to two random fields, that it would be present in both of those. I could also ask, well, what's the probability that I'd go out to two fields and it would be totally absent? Well, that's going to be Q times Q. And so roughly 46% of the time, I would expect it to be absent. And then we can also think about, well, what's the probability if I went out to two fields and it was present in the first one and absent in the second one? Well, if it's present in the first one, that's P. Absent in the second one, that's Q. I expect that to happen roughly 22% of the time. And then likewise, I can say, well, what's the probability if I went out there and it was absent in the first one, and then it was present in the second one? Okay, that makes sense. Again, 21, 22% chance. And so what we have now is we have a model that is describing the probabilities for any two fields that we would go to, any two patches of alfalfa that we would go to. The probability here that it's present in both of them, it's absent in both of them, it's present in the first one, absent in the second, absent in the first, present in the second. Yeah, absent in the first, present in the second. And if we were to add all these numbers together, that plus that plus that plus that, it's going to equal 1. Probabilities will always sum to 1. So what's kind of interesting, and maybe some of you have kind of caught this, is that what have we done here when we've done this little arithmetic here? We've done the probability that it's present in both of them is P times P. Well, that sounds to me like that's P squared, right? The probability that it's absent in both, well, that's Q squared. And then I have the probability that it's present, and then times the probability that it's absent. And then the probability that it's absent times the probability that it's present. And so I don't know how familiar this looks to you yet, and we also know that the sum of all those is going to equal 1. Let me make myself bigger because I'm rambling now. Okay. Well, we could rewrite this as that. And that should look familiar to a lot of you because in general genetics class, that's Hardy-Weinberg equilibrium. And a lot of times people get all bent about Hardy-Weinberg because books always are like, here are the assumptions of Hardy-Weinberg. And they're all totally unrealistic assumptions. Total random mating, infinite population size, well, that's impossible, that's ridiculous. No mutation, there's all these different assumptions that people kind of get caught up in when they're dealing with Hardy-Weinberg. But Hardy-Weinberg is just simply a model, and it's a model based upon these simple probabilities. So, you know, in Hardy-Weinberg, we're thinking about, you know, big A versus little a, or being a heterozygote. That's the same thing as us asking, what's the probability that the butterfly is present in both patches versus absent in both patches? Present in the first, absent in the second, absent in the first, present in the second. That's all Hardy-Weinberg is it's just a simple statistical model, and it tells us what our expectation is. And all those assumptions are in there simply because it's a statistical model, and we're assuming that they are random variables drawn from some distribution. But maybe we digress a little bit. I don't know. Let's go back and let's think about what else we can do here. So these are pretty straightforward, right, on how we calculated that. If I wanted to know what is the probability that if I were to go out to 70 patches, let's say, and I want to know what is the probability that it's going to be present in 70 patches that I would go out in the field to. Well, it's going to be the probability that it's present times the probability that it's present times the probability that it's present, and we're going to do that 70 times. The easier way to do that is to simply say p raised to the power of 70. Okay. That is the probability that it's going to be present in 70 selected patches of alfalfa that we might find in the Great Basin. Very, very low probability, but it has a probability. Okay. Likewise, we could say, well, what's the probability that it's absent in all 70 of those patches? And sometimes I have field seasons that feel that way, but let's do that. Okay. Well, just eyeballing that, we can see both of them are pretty improbable. But actually, it's way more probable that they're going to be absent in all 70 patches than that they're going to be present in 70 patches. Okay? And so even though the probabilities are small, there's still a really big difference. It is way more probable that you're going to have no butterflies present than butterflies present everywhere. Okay? And so let's make this a little bit more complicated, if you will. And let's think about, what if we knew that there were 172 patches of alfalfa out west in the desert? And of those 172 patches, we want to know the probability that our butterfly, our handsome little Melissa blue butterfly, we want to know the probability that it's in 70 out of those 172 patches. We don't care which 70 they are. We just want to know what is the probability that they're in 70 out of 172 patches. And so the first thing that we need to think about is, how many different ways can we get 70 patches out of 172 patches? And to do that, we take the product of the total number of patches, and so what we would do is we would, let me go up here, so we would say I want 172 times 171 times 170, and so on and so forth, all the way down to 103, all the way down to 103 patches. And so what we can do is we can use that little shortcut. If I were to just type 172 colon 103, it's going to count as integers from 172 down to 103. Okay. And so what we want to think about is what are the number of unique ways that we can get 70 patches. And what I mean by unique ways is we don't really care if we first observe it in that patch and then we observe it in that patch. Let's say you have two patches, patch A and patch B. When we simply just take the product of all of those, right? That's a huge number, 2.2 times 10 to the 149th. That's all the different ways that we can get 70 out of 172 patches. But what it's not considering is that there are multiple different ways that we could get those patches. So again, if we think about patch A versus patch B, we could first observe it in patch A and then observe it in patch B. But we could also, just because of how we're driving around the desert, we could first observe it in patch B and then observe it in patch A. And so what we really want to know is how many unique ways can we get 70 patches occupied? And what we'll do for that is we will divide that by the factorial of 70. So 70 times 69 times 68 times 67, 66, 65, so on and so forth, all the way down to 1. And so when we do that, now we have still a really, really big number. There's a lot of ways that 70 out of 172 patches that can be occupied, but it's not nearly as many ways as when we didn't account for the fact that there's a lot of different ways that we could get that basically the same value. I mean, if we go back to thinking about our coin tosses here, there's two different ways to get heads or tails, right? First you can flip a head, then you can flip a tail, or first you can flip a tail, then you can flip a head. But at the end of the day, it's still one head and one tail. We don't care about the order. And that's what we're doing here is we're removing, not the problem, but the fact that just taking the product here, that's only going to give us all the different ways we could get 70 out of 172. Whereas here, we're only interested in the unique ways that we can get 70 out of 172. So this is what is referred to as the binomial coefficient. And it would be often written as a big parenthesis of 172, and then we would say 70 here. And we would read that as 172 choose 70. And this is again what is known as the binomial coefficient. So R is a statistical programming language, and it shouldn't be entirely surprising to anyone that there might actually be a built-in function that'll do the binomial coefficient for us. And that function is called choose. And so if I were to just type in choose 172, 70, those are the two arguments that are going to go into choose. Again, we can always hit question mark choose, and it'll tell us what our functions are doing. And somewhere in there is choose nk. N is the total number of things that we're potentially sampling from, and then k is the number of samples from that. So we have 172 fields out in the Great Basin, and we want to just think about how many different ways can I get sample 70 of those 172 patches. And so if we go ahead and we run that, we get the exact same answer that we got up here, okay? And so that's great. So what we have done now is we figured out all the different ways that we can find 70 from 172. But we haven't really figured out the probability that Melissa is in exactly 70 of those patches. And so to do that, we're going to want to think rather carefully about how we're going to deal with the probabilities. So first what we need to do is we need to calculate what is the probability that it is found in exactly 70 patches. And we've already done that up here, right? And so that is going to be the probability that it's in 70 patches. Now we're going to have to multiply that by the probability that it is absent in the remaining 102 patches. And so we will go multiply that by Q to the 102. All right? And so this is the probability that it's absent in 102 patches. This is the probability that it's present in 70 patches. And now we're going to multiply that by our binomial coefficient. And we're going to multiply it by that because all we've calculated here is the probability that it's in exactly these 70 patches and absent in exactly these 102 patches. But what we have is we have 172 patches total, and we don't care which 70 of them are occupied. We just want to know the probability that any 70 of them are occupied and any 102 of them are unoccupied. So we're going to multiply that number by all the different unique ways that we could get that, and that's where we're going to use this binomial coefficient. And now here is the probability. And so interestingly, when we just ran this, that would have been for very specific patches. Maybe, you know, your 70 favorite patches are occupied and the 102 remaining patches are unoccupied. But since there's a bunch of different ways that we could get 72 occupied and 102 unoccupied, we multiply that by the binomial coefficient. So any 70 specific patches, incredibly low probability that, you know, if I had a list of the 172 patches and I arbitrarily put a check mark next to 70 of them, that's the probability that I would be right. Really, really low that Jim would be right on that one. However, when we multiply it by all the different ways that we could actually get 70 patches, okay, well now we have maybe you know, a probability that clearly is a lot bigger. It's like what here? So it's a 0.35% chance that exactly 70 patches will be occupied. Okay. Hopefully that's kind of clear as to how we're dealing with probabilities and how we're actually able to calculate the probability of any kind of series of events from happening. And so likewise, we could say, well, what's the probability that, you know, maybe it's 60 patches instead, right? And then we could just say, well, if it's present in 60, that means that it must be absent in 112, and our new binomial coefficient will be that. And so, ooh, now we have a 4.6% chance that 60 patches will be occupied, and so on and so forth. And so what we've been doing here is that we've been modeling each patch. It's either occupied or not occupied. So our data, if it's occupied or not occupied, we would write down that Y, our data, are distributed as a Bernoulli. And in our case here, it would be 0.32. This is the formal way that we would describe what we've just been doing now. Y is a random variable drawn from a Bernoulli distribution with a probability of 0.32. And so this whole idea of thinking about explicitly that we're measuring the probability of things, that's going to be the cornerstone of really most of the stuff that we do. That's what likelihood is. Likelihood is really the probability that we're observing something. And we're asking, you know, what is the probability that 70 patches out of 172 would be occupied? Or what is the probability that 60 versus, you know, versus something else is going to be occupied? When you have a series of Bernoulli draws, when you have a collection of Bernoullis, that is what is referred to as the binomial distribution. Okay, so you can think about the Bernoulli as being a special case of the binomial. And the binomial is simply a series or a collection of Bernoulli draws with a set number of trials. It's often referred to as a trial. So you could think about every time we would go out and we would visit one of those patches of alfalfa, we are doing a Bernoulli draw. If we go to all 172 of them, well, that's 172 trials. And what we could call the presence of the butterfly as being a success. We found our bug that we were looking for. And if the bug isn't there, we could think about that as a failure. And that's what the binomial distribution is doing. And so let's go ahead and we can just kind of take a break and digest this, and we'll come back and we will think about the binomial distribution, hopefully clearly. Okay, well let's think more now that we've learned that a bunch of Bernoullis is a binomial, and that means that we can really calculate. Thinking about, again, sticking with the butterfly example, we can calculate the probability that it's in 0 patches out of 172, probability that it's in 1 patch out of 172, so on and so forth. And since we got a computer, why don't we have the computer do the work for us? So we already have P, but I'm going to go ahead and I'm going to retype in P. Okay, so that's the probability that it's present. I said that there were 172 patches. And then let's think about I'll use the letter K to be the number of successes or the number of patches that were occupied. And I'm going to let that go all the way from 0 to 172. Okay, so again, that little colon there, that's just creating a vector of numbers starting at 0, ending at 172. Just as an aside, one thing that you will always want to kind of keep track of when you're dealing with discrete values is that notice if there's 172 patches, that means that there's actually 173 different possibilities, because it being absent from everything is one of the possibilities, right? So the first value is 0, the second value is 1, so on and so forth, which means that the 173rd value is 172. And this sometimes can kind of trip people up at first because, you know, you don't always think about the fact that you need to have this space being held for the possibility of there being 0. So out of 172 patches, there's actually 173 different things that we might observe. It could be absent in all patches, present in only 1 patch, present in only 2 patch, so on and so forth. And so we could calculate then the probabilities. I'm going to create an object called the probs. And I'm going to go ahead and I'm going to just plug it into this formula that we have been playing with before. So if we're trying to calculate the probability that the butterflies are present, it is going to be P to the K, right? So the probability, we're going to be able to calculate the probability that it's in 0 patches, the probability that it's in 1 patch, so on and so forth. And we're going to multiply that by it being absent then in the remaining patches. So we're going to start with 1 minus P, right? Which again is sometimes referred to as Q, but let's just keep it simple and keep it at 1 minus P. Here, I'll even put some spaces in here so we can follow along. 1 minus P, this is the probability that it's present in any randomly selected patch, which means that this is the probability that it's absent in any randomly chosen patch. Again, 0.68 plus 0.32 is going to sum to 1. Probabilities are always going to sum to 1. And then I will raise that to the power of what? It'll be the power of the total number of patches minus the number of patches that are unoccupied. And then I need to multiply it by that binomial coefficient so that I can think about all the different ways that I might observe something. And so I will say choose what? I will choose to move this over. I will choose NK. Okay, so again, there's 172 patches, and then K is this vector. So if I were to just run that, we can go ahead and we can look at some of these earliest values up here. Well, if there's 0 patches that are occupied, how many different ways can I get 0 occupied patches out of 172? Well, there's only one way I can do that, because there's only one way that everything can be butterflyless, if you will. And so that's why, that's what that binomial coefficient is. If there's only going to be 1 patch out of 172 occupied, well, there's only 172 different ways that that could possibly happen. But then as you start to increase, well, how many different ways could I have 2 out of 172 patches occupied? Now we start getting into a much larger number, and so on and so forth. So by running this line of code, because as we mentioned in the R tutorial, R is conveniently vectorized, which means that we can stick a vector into a formula like this, and it'll do the mathematical computations across all of that. So I'm going to go ahead and I am going to do that. So now I have a vector of probabilities. Okay. And again, the first value, that's the probability that all the patches are unoccupied. That's the probability that 1 patch is occupied. This is the probability that any given 2 patches are occupied. So on and so forth. If we were to take the sum of the probs, it's going to sum to 1. Probabilities always have to sum to 1. Okay? And so with a binomial draw, we have a set number of trials, 172, and we can think about all the different ways that we could see butterflies out of those 172 patches. The probability of all of those different kinds of ways is always going to sum to 1. And so I'm going to go ahead and I'm going to plot this so we can take a look at this. And for our purposes here, and I would do the same thing if we were in class, I'm not going to plot it down here, which is the default, because it always looks crummy and the margins are way too big. So I'm going to call up a new plotting device for myself. On the Mac, it's Quartz. I believe on a PC, it's just called Window. And if you do the parentheses, what's going to happen is I have this floating around window that's no longer in RStudio. And it's not really that big of a deal when you're playing at home, but over the course of the semester, I'll always be calling up new Quartz windows, and that's just because the windows are bigger and it's easier for lecturing purposes. So I'm going to move that out of the way. You'll notice that I often look up here. That's because I have a separate computer screen. And so I'm going to move this out of the way so I can actually see what our code is. And I'm going to type a function called plot. And plot's going to want the x-axis and it's going to want the y-axis. So the x-axis is going to be 0 to 172 because that's what we were interested in. Either 0 patches being occupied, 1 patch being occupied, 2 patches, so on and so forth, all the way up to all 172 patches being occupied. So I'm going to do that. I'm going to say plot that. And the y-axis, I want it to be the probs. So I go ahead and I do that. And this is what it looks like. Okay, so you can see that, and these are patches occupied down here, and here are the probabilities here. We can see that it's really not very probable that you're going to have only a small handful of patches occupied, and it's really not going to be all that probable that you have tons and tons upon tons of patches occupied. So I'm going to play around a little bit more with this plot. I'm going to zoom in to just this region. And here again is where there's just a learning curve as you're playing with R. And so and all this code is available to you, so you can kind of start to explore and play around. But I'm going to make this exact same plot, but I'm going to say that the x limits, which is an argument called xlim, and I'm going to give it the lower value and the upper value. So again, I got to tell R that I'm giving it a vector, because it's going to be a vector of 2, the lower value and the upper value. And I'm going to have it only plot out the region between 35 occupied patches and 75 occupied patches. So now I'm zooming in a little bit more, right? And you could look at this and say, oh, well, that looks kind of normal. And it's like, yeah, but it's not. That is describing a binomial distribution. And here are the probabilities. And we can look at this and eyeball it and see like, oh, well, right around here, that is the most probable number of occupied patches, which appears to be somewhere, I don't know, 56, 57-ish. We'll get to in a minute how to figure out exactly what that value is. But we can see that there is a range of most probable number of occupied patches. And once we get out to these extremes, either way, it becomes very, very improbable that we would observe that. But they all have a probability. There is a probability that we would have no patches occupied, and there is a probability that we would have 172 patches occupied. But the most likely number of patches occupied are clearly somewhere here between the values of, say, 35 and, I don't know, 35 and 65-ish, 45 and 65, somewhere around there. Those are just the more likely ones. And then what I've also included on the code that I've given you is just a few other arguments that we can put into that plot function to make it look prettier. And so something like this. And so again, what am I doing? I'm plotting 0 to 172 on the x-axis. The probabilities are on the y-axis. I'm giving it its limits. I'm putting in this extra argument in here called type. And I'm saying type H, which means you want it to look histogram-ish. It's not truly a histogram, but it's histogram-ish. It'll look like a histogram. I'm going to use this argument LWD, which is line width, which is going to make the lines fatter so that we can see them more pretty when we're looking at our plot. And then I'm going to give it a title. And the title I'm going to give it is the probability mass function, because that's what we're describing right now. And then this final argument, lend, is for line endings, and it's going to tell it that I want it to have square line endings. And so if I went ahead and I ran that code, now I got to find my quartz window. Here it is. It'll look something like this. So again, it's histogram-y because it's bars. These are nice fat lines because I said I wanted the line width to be 10, and they have square ends because of that lend argument. At no point in this course will you ever be graded on how pretty your graphs are, but to make them somewhat aesthetically pleasing, I decided to put those in there, so I thought I'd explain what those are. And so this right here is what the math, the arithmetic that we did when we did this, is what's known as the probability mass function for a binomial distribution. And if we wanted to see formally how it would be described mathematically, it would look something like this. In fact, if you were to do a Google search for binomial distribution and look at the Wikipedia site, you would see that on the right-hand side of where it talks about distributions, PMF, probability mass function, there's our binomial coefficient, which figures out all the different ways that we could observe k number of successes out of n number of trials. Here, p to the k, that's the probability of success. And then here is the probability of failure. Okay, and so again, you know, sometimes people use q, sometimes people use 1 minus p. It's all the same thing. It's the probability mass function for a binomial distribution. And so that would mean that for this example here, if we were to go out and look at those different fields or patches and ask if they were occupied or not, what we would do is we would formally write out how we are modeling the data that we are collecting. And so if I can just make sure that I'm on the right page. Okay. What we would say is that we would say that our data are random variables drawn from a binomial distribution with a set number of trials, and we're interested in and the probability of success actually occurring. And so we could write this in a formal kind of framework. We could say that our data are random variables drawn from a binomial. And then in parentheses, there's going to be two important parameters in this model that are going to describe the shape of that model. It's going to be n, the number of trials. And so in this case, we have 172 trials, and our p parameter is 0.32. And so that would be the formal way that we would write out our model and what we would use to describe the probability of any particular events occurring. And so let's go back and look at that object that we created called the probs. And let's say that we were interested in knowing what is the probability that we would find a butterfly in 60 or fewer patches. Okay, and so we have this long vector called the probs, the dot probs. Okay, here is our long vector over here. And again, this is the probability that it's in 0 patches. This is the probability that it's in 1 patch, so on and so forth. So if we wanted to know what is the probability that it's in 60 or fewer patches, we would want to first pull out just those probabilities. And so it's going to be the very first value all the way up to the 61st value. Because again, the first value is 0, which means that the second value is 1, which means ultimately the 61st value is the probability that it's in 60 patches. And so now we can go ahead and we can run that, and here are all these probabilities, right? The probability that it's in 0, probability that it's in 1, probability that it's in 2, so on and so forth. And so if we wanted to know what's the probability that it's in 60 or fewer of those patches, we would just simply take the sum of that, and it's 0.81. So that is our probability that it's going to be in 60 or fewer patches. Okay, and so again, R is a statistical programming language, and so it shouldn't come as a great shock to anyone that there might be a built-in function that'll actually do this for us. We don't have to type out this probability mass function. Now that we understand what it was, and from the ground up, we basically invented or reinvented this distribution, right? This binomial distribution. We don't need to type in all of this each time. We can use a built-in function, and that built-in function in R is what's called dbinom. And dbinom has a couple of arguments that we need to consider. X, size, and probability. Those are the important ones for right now. So X we can think about as the number of successes. So maybe the number of patches that are occupied by this butterfly. And so we could say X equals, let's say 0, just for starters. Size is what? Size is the total number of trials. In this case, the total number of patches, 172. And then we have our probability. Probability of success is 0.32. And so that's the probability that it's going to be in 0 patches. That is the same answer that we got when we did it longhand. Okay, so the built-in function is going to do our work for us. A little bit of technical difficulties, I'm back. So we can use this built-in function, dbinom, right? And again, this is giving us the same answer that we got when we did it by hand. And so again, this is the probability that it's in 0 patches, which is the exact same answer that we got when we did it by hand, if you will. And so again, going back to the question of, well, what is the probability that it's going to be in 60 or fewer patches? Well, we could take the sum of those first 61 values, because the first value is 0, which means the 61st value will be 60 occupied patches. We could do the same thing using the dbinom, but here we're saying that the number of successes is from 0 to 60, and again, that colon there will simply just count from 0 to 60 as integers. And so if we were to take the sum of all those probabilities, we get 0.814, which is the same thing we got when we did it, when we actually programmed in our own probability mass function. So another thing that we might be interested in knowing is what the most likely number of patches to occupy is. So remember when we looked at our plot, gotta find my plot now, right? We can eyeball it here. Well, somewhere over here is the most likely number of patches occupied. And so we could kind of squint and look at that. That can be kind of challenging if it's a very complicated graph, if there's a lot of things going on. And what we can do is we can use just a little bit of R coding. We have this object called the probs. Let's just go back to the probs. And if I wanted to know what is the most likely, so it would be the one, which value there is the most probable, I could take that vector for the probs, and I could ask, what is the maximum value? Okay, so one of those, the most likely outcome, has a probability of 0.065. If I wanted to know exactly what value that was, this is where we can use a little bit of some basic R functions. I could say which the probs is super duper equal to the maximum of the probs. And recall that the function which will tell you what is the value for the index to find a certain condition. So here it's going to tell us what value of those 173 values is the maximum value. And if I do that, I get the 56th value. The 56th value will correspond to 55 patches. Because again, the first value is 0 patches, the second value is 1 patch, so on and so forth, which means the 56th value will be 55 patches that are occupied. So if we were to look back here, this highest peak right there, that is 55. Okay, so that's a way that we can figure out the most likely number of patches that are occupied. Okay, good. So let's go back to that question that I posed before, which was, what's the probability that it's in 60 or fewer patches? So what we've done here is we've taken the sum, obviously, of it being in 0 patches, of it being in 1 patch, being in 2 patch, so on and so forth. And so what we can do next, or another way that we can think about that, is all we're doing is we're summing up 0 through 60, which means that if we wanted to know 55 patches, it would be summing up 0 through 5. And so we can do this in a brute force way. I'm going to create an object that I'm going to call cumulative.probs. And I'm going to use a built-in function in R that calculates the cumulative sum And so in other words, it'll start with the first value, and then it will add the first and the second value, and then it will add the first, the second, and the third value, so on and so forth. So I'm going to go ahead and I'm going to do that. And so now I have cumulative probabilities. So this is the probability that it's in 0. This then would be the probability that it's in either 0 or 1. The next value would be the probability that it's in 0, 1, or 2. And so we can look at what that looks like. Here, I'm just going to cut and paste from the code that I've given you. We're just going to C-bind them together so we can look at them like they're a table. And so here is the here are 0 patches occupied. This is the probability that you would have 0 patches occupied. And here's the cumulative probability, which is going to be the same because right now we only have 0 patches occupied. But now when we get up to 1 patch occupied, here is the probability that exactly 1 patch will be occupied. The cumulative probability is the probability that either 0 or 1 patch will be occupied, and so on and so forth. So, you know, for example, if we go to where we talked about our 60, this is the same value that we got when we took the sum of the first 61 values from the probabilities. The probability that it's in exactly 60 patches is that, but this is the probability that it's in 60 or fewer patches. Okay. And so that's what's known as the cumulative probability distribution, or the PDF. And on the notes that I've given you, there's actual, we could formally kind of show what that looks like in the maths. Here you can see this is just simply the probability mass function. The only difference is that we're taking the sum from 0 up to a particular number of successes. And so this is the cumulative distribution function for a binomial. And there is a built-in function that'll do that for us as well, so that way we don't have to deal with saying sum, for example. And that function is called pbinom. And what pbinom wants, let's go ahead and just say question mark pbinom, so we can think carefully about what we're doing here. Okay. Pbinom is going to want what? It's going to want some kind of a vector of quantiles. And then, of course, it's going to want the size, how many trials were there, and then the probability. And so in this case, when we're interested in the probability of there being 60 or fewer, we could use pbinom. We could say 60, which is going to be the quantile of interest. The size is 172, and our probability is 0.32. And again, I don't have to type out all the arguments because I'm putting them in there the exact same order that the function is expecting them to be. But maybe just to, for one last time, to just be careful, let's go ahead and put those arguments in there so we can follow along with no problem. Oops. Oh, Q. Pay attention, Jim. Okay, and so here is the cumulative probability of there being 60 or fewer patches occupied, which is the exact same answer that we got when we used the probability mass function and took the sum. When asked questions like what is the probability of it being in 60 or fewer patches or more patches or whatever it might be, it's always a good habit to get into to just start using that cumulative distribution function, because we're not going to be able to play this little game where we take the sum of all the different probabilities when we start dealing with continuous distributions, because any given value is infinitesimally small. So let's take a quick look at what the cumulative distribution looks like. I'm going to just go ahead and plot it. and I'm going to look for my window here. Okay, so here's what the cumulative distribution looks like, and here you can see that you're adding together more and more and more probabilities, and I've put this red little dotted line here just arbitrarily. I put it there, and that's where you're 95% confident in something. So where something is 95% probable. And so it's really quite close to what our 60 was, right? And so it's probably somewhere, if I were to go to 64, 65 patches, there. I'm 95% confident that there's going to be 65 or fewer patches occupied based upon the fact that we have 172 patches and the probability that any given patch is occupied is 0.32. And that's how we can use that cumulative probability distribution. Okay, so we can do that with any value. What's the probability that, 20 or fewer patches is occupied? That's the probability that 20 or fewer patches is occupied. Not very probable, which isn't terribly surprising, because if we look at, we don't even have that. We know that when we get to a very few number of patches occupied, we really start to have an incredible low probability. So there's a real low probability that we're going to have 20 or fewer patches occupied. The cumulative distribution and the probability mass function are essentially telling us the same information. It's just done in a slightly different way, because the cumulative is it's doing all that addition for us from left to right. So one thing that can be tricky, and it's important to keep this in mind, is I've been very careful, or at least I've tried to be very careful, when I've asked that question, what is the probability that it's in 60 or fewer? Okay, which means that if this is the probability that it's in 60 or fewer, that means that the probability that it's in more than 60 is going to be 1 minus that value, right? So the probability that it's in more than 60 is 0.18. The probability that it's in 60 or fewer is 0.81. With discrete distributions, you have to be very aware and cautious about that whole thing of being equal to or less than, or greater than, or greater than or equal to, because it's going to determine exactly where the cutoff is going to be. So for example, if I wanted to know what is the probability that it's in 60 or more patches, what I would need to do is I would need to take all that probability mass that it's in 59 or fewer and subtract that from 1. So this right here, that is the probability that it's in more than 60 patches. If I wanted to know what is the probability that it's in 60 or more patches, I would have to change this number here to 59, because I'd basically want to exclude all the probability mass that has anything to do with a number that's less than 60. With these functions in R and all computer languages that I know, it's always going to read from the left to the right. So you have to be aware of, or at least cautious when looking at a question or trying to solve a problem. You have to think really carefully about whether it's equal to or greater than, or just simply greater than. Okay? An alternative way that we could do something very similar to this is there is an additional argument here, you'll notice, which is lower tail. So by default, lower tail equals true means that it's going to look at all of that mass on the left side of the distribution, working from left to right. If I said lower tail equals false, dot tail equals false, it's going to do that arithmetic for me. Okay, so just be aware of that. You can say lower tail equals false, but again, you have to be really, really careful with how you're defining where the cutoff is. So this code right here, that's telling me the probability that it's in 60 or more, whereas this is the probability that it's in more than 60. Okay, again with that lower tail equals false. If I didn't have that argument in there and the default is lower tail equals true, that is the probability that it's 60 or fewer, okay? Whereas this is the probability that it's in more than 60. And so just be aware of that. It can throw people off, and it takes maybe just a little bit of practice to kind of think about how to deal with that. Okay, well, good then. Where are we? Let's talk about stuff. Yeah, and so let's just really quickly just take a look at the binomial. We've looked at one binomial distribution based upon our parameter setting of 0.32. And I'm going to just create another plot here so we can just look at how the shape of the binomial distribution changes as a function of the p parameter, or that probability parameter. And so here's the probability mass function where p is equal to 0.32, and this is the distribution that we have been playing with. Okay. As we decrease that p parameter, things are becoming less and less probable. And so it's going to shift the mass of that distribution closer and closer to 0. Here I'm making it at 0.05. And then here, finally, I'm making it at 0.005. Okay, so much, much lower. And actually, there's a typo. There's a typo. Way to go, Jim. Let's do that again. Okay, so here is at 0.1, decreasing the probability. Now 0.05. So now it's becoming really unlikely that you're going to see anything. And most of that mass then is over here near 0. Now 0 is actually a pretty probable outcome. And then when we get a really, really small probability, now most of our probability mass is at either 0 or 1 patches occupied, and it's incredibly unlikely to have any of these other patches occupied. So the shape of the binomial distribution is going to depend on what those parameter values are, and eventually when that p parameter gets really, really low, it's going to get slammed up next to 0. And so based upon that, if we have an estimate for our p parameter, we can model these types of data as random variables drawn from a binomial distribution, and we can come up with some expectation as to what we expect the certain number of, or however many number of patches to be occupied. So let's play with that and let's think about that, and then we'll revisit a few other things so we can think clearly about how to deal with the binomial distribution. Hopefully you've played around a little bit now with the dbinom function and the pbinom function and understand how to use them to come up with some kind of a prediction or a probability that we're going to observe something happening. Up to this point, the parameter, the p parameter or pi parameter, but the probability parameter I've given to you, right? So based upon many previous years of work, I have this estimate for that p parameter, which is that the probability of a patch being occupied is 0.32, and that's what we've been using to think about the probability of 60 patches being occupied, or 50 or more, or whatever we might be interested in learning. But what we haven't talked about is, well, how do you estimate that parameter? And how we estimate the parameter for the binomial distribution is we take the total number, once we're collecting data, and we would look at the number of successes, so the number of occupied patches in our butterfly example, divided by the total number of trials, or the total number of patches in our case. And so if we continue to think about the binomial as being the number of successes given a certain number of trials, the estimate, the maximum likelihood estimate for that p parameter for a binomial is simply the number of successes divided by the total number of trials. Okay? And so conveniently it's essentially the arithmetic mean, right? It's how many yeses versus how many total attempts. Right. And so let's think about that. So first of all, this is me telling you that is the maximum likelihood estimate, but I hope that you're not satisfied with the fact that it is the maximum likelihood estimate simply because I said it was the maximum likelihood estimate. Let's actually understand what we mean and how we can come up with these maximum likelihood estimates and why certain things are maximum likelihood estimates. And to do that, we have to understand likelihood. And so what I'm going to do is I'm going to stop talking about butterflies for a few minutes. And I want to go back to just thinking about coin tosses, because it's really easy to think about a coin toss because everybody at some point in their life has probably flipped a coin. And let's say, for example, you were to flip a coin 100 times and you observe 60 heads and 40 tails. Okay? And so let's model this and assume that heads are a success and tails are a failure. But if you flipped a coin 100 times and you observed 60 heads, your maximum likelihood estimate for that coin is going to be 60 divided by 100, which is 0.6. So that is what that would be the maximum likelihood estimate. But there are likelihoods or probabilities that you could ask, well, what's the likelihood that I would get 60 out of 100 coin tosses if the probability was 0.5, or if it was 0.4, or if it was 0.3? And so what I want to do is I want to reconstruct what is the likelihood of our data given a particular parameter value across a number of different parameter values. Okay? And so what we can ask then is, what is the probability that I would get 60 heads out of 100 trials, or we could think about it as 60 heads and 40 tails given a particular value of that p parameter? And so I've written a little bit of R code to kind of explore this, and this is an example of where, you don't obviously have to fully follow all the code, but I'm going to make things bigger. I want things to be bigger. There we go. Okay. And so what am I going to do? I'm going to think about possible values for the p parameter. And so again, with our example with the 60 out of 100 heads, we know that the maximum likelihood estimate is 0.6, but let's explore how probable it is that we would get 60 out of 100 across a whole range of different p parameter values. So I'm going to create an object called p's, and I'm going to use a built-in function called sequence, S-E-Q. And I'm going to ask R to provide for me a sequence from equals 0.00001, so a really, really small value, something that's incredibly improbable. I'm going to go all the way up to a really big value for that p parameter, right? That p parameter has to be constrained between 0 and 1, so these are really close to 0 and 1. And then I'm going to ask for 1,000 values. And so all R is going to do is it's going to count from this number to this number at equal increments, and it's going to give us 1,000 values from that minimum to that maximum. Okay, and so here's all those values. There's 1,000 of them. All right. And so now what we can do is, given the scenario that we flip the coin 60 times, or I'm sorry, we flipped the coin 100 times and we got 60 heads, we can ask, well, what is the probability that I would get 60 out of 100 if the p parameter's value was 0.001? And then what's the probability I would get that if the p parameter was 0.001 and then 0.002 and so on and so forth. And so what we're doing here is we're holding our data constant, and we're going to explore what the probability is of our data given a particular parameter value. And so I'm going to go ahead and I'm going to plot that. I've created that PZ thing. And I am going to say plot. The x-axis is going to be the values, the possible values of p. And then the y-axis is going to be the probability density of getting 60 out of 100 given that particular value. And so generally, when we're thinking about likelihood, it's often written explicitly. You know, again, with our example, we had 60 heads and 40 tails. We could ask, what is the likelihood that we would get 60 heads? What did I say in that? Okay, and 40 tails. Those are our data. Given what? Given some value for that p parameter. And so when we think about likelihoods, what we're going to want to think about is what is the probability of our data given our parameters? So this is kind of a nice generic way. Probability of our data given the parameters. Okay, it's a nice kind of generic way to always be thinking about your data when you're modeling it and you're estimating parameters. And so what I've done here, whoa, has made everything disappear. What I've done here is I'm going to explore across all 1,000 possible values of the p parameter. I'm going to ask, what's the probability that I would get 60 heads out of 100 coin tosses? And so I'm going to go ahead and I'm going to plot that. That's not what I want. Where is it? There. Okay. And so here is the likelihood of our data given the parameters. Okay. Again, the likelihood of the data given the parameters. Our data is 60 heads, 40 tails. And so here you can say, well, what's the probability that I would get 60 heads and 0 tails if the probability of getting heads was 0.2, let's say? Well, that probability is really, really close to 0. That's really, really improbable. What if the parameter value was 0.4? Still really, really improbable. But you'll notice when you start getting here around what our maximum likelihood estimate is, those are the most likely values for our parameters. And what we're interested in when we're calculating the likelihood is we're usually interested in calculating the maximum likelihood. So what we'd like to know is what p parameter here, what value here is the most likely value for that parameter given our data. And we can basically look at what we're trying to do. That is the most likely. That is the MLE. That is the maximum likelihood estimate of our data. Okay? And so what we want to know is, well, Jim told us that we could calculate this as a 0.6 because he told us that if we got 6 heads or 60 heads out of 100 coin tosses, the maximum likelihood estimate is 0.6. And that's great, but let's demonstrate to ourselves that it actually makes sense why that is the maximum likelihood estimate. Because whenever we're dealing with distributions, we're always going to be dealing with trying to estimate parameters, and generally we're interested in the most likely value for those parameters. So the first step is let's revisit and think about, well, how did we draw this, right? We drew this using the dbinom function. we know that the d-binom function is the probability mass function for the binomial distribution. So this curve right here, based upon our data, this curve is being described by that probability mass function. And since we have the underlying math of what that probability mass function is, we should be able to determine how do we figure out what value of p is at this very, very top here. And this is, we're going to do a little bit of math, and this is really the only time this entire semester where we're actually going to do real math. But since we have a function that describes that curve, we could imagine that if we want to figure out what this value is, we could take that function that's describing this curve, we could take the derivative of that function, right? That's why calculus was invented. We can take the derivative, and then we can solve for where the slope is equal to 0, okay? So recall that the derivative is telling us what the slope is of any line that's tangent anywhere along that whole curve. And what we'd like to do is we'd like to solve for a point where the slope of that line tangent to that curve is equal to 0. And the only place that that's going to happen is right at the very top. It's going to be the maximum likelihood estimate. And so let's just, for fun, because such things are fun, just to prove to ourselves that we feel comfortable where these maximum likelihood estimates are coming from, I'm going to just walk through really quickly the calculus. And all of this is in the notes as well. But I always find it sometimes, or at least not always, but oftentimes I find it easier to follow along with written math if somebody is kind of walking me through it. So let's start with what was responsible for drawing that curve. Again, what is responsible for drawing that curve? And it's the probability mass function for the binomial. And so what it is what? It's going to be the probability of a success, right, times 1 minus p to the n minus x, right? And so that's the probability mass function for a binomial. Sure, we could multiply it by the binomial coefficient to think about all the different ways that we might do it, but we flip that coin 100 times. We know we're only interested in our sample, so we don't really care about all the different ways that we could have gotten 60. And also that binomial coefficient is a constant, right? It's a number, so it's going to get dropped out anyways when we start doing the little bit of calculus on it. And so this right here is the likelihood of our data given our parameters is that. So this is going to be, this is our starting point right here. So the first thing we'll do is, here we're multiplying and stuff like that. First thing that we would like to do is to make that actually easier for ourselves. So instead of thinking about the likelihood, we're going to think about the log likelihood. People like to think about log likelihoods because all likelihoods are is a product of a bunch of probabilities. And since probabilities can be small, and if you start multiplying a bunch of small numbers by a bunch of small numbers, it isn't terribly convenient. And computationally, your computer will end up rounding it to 0, and you'll go nuts just trying to do all that multiplication by hand. And so generally, we like to put this all into units of log, because multiplication in the log universe is simply addition. And so what we can do is, instead of thinking about the likelihood, we can think about the log likelihood. And so let's go ahead, and if that's just the likelihood is that, let's say that the log likelihood is going to be the log of p to the x plus the log of 1 minus p to the n minus x. Okay, so all we've done here is, and this is why I rewatch all of these. So although they are long, imagine how I feel. I have to not only say it, but I have to watch it multiple times. That's a mistake. I have to redo this little part, and it's just how I've written the math. Actually, none of the other stuff I did over the whole course of the now deleted the now deleted part of the lecture was wrong, except for this one little spot right here. And maybe some of you saw it. This is wrong. This little parenthesis should be there, right? That's where that parenthesis actually belongs. And that means that we also need a parenthesis that goes like this, right? Because the whole thing is being logged. So 1 minus p to the n minus x, that's all being taken to a log scale. And so I just miswrote it, so we're gonna do it all again. Okay, so, this is actually an opportunity to notice something else that I've been kind of throwing around kind of loosely, likelihood. And up to this point, when we've been playing with D binom and C binom, I've been trying to be very explicit that it's the probability of an event. And so what I've ended up doing in the last 5 minutes, just I think because I'm just used to kind of talking in a more casual way amongst kind of statsy nerdsy people, is I'm using likelihood and probability interchangeably. And actually that's fine for a discrete distribution. Likelihood is often, or is also used when dealing with continuous distributions, and when we deal with continuous distributions, as we will see, we're not going to really be talking that much about the probability of any given observation. We're going to talk about it as the likelihood, because it's going to be kind of set up in a slightly different way. For our purposes today, we can interchangeably use likelihood. So we can think about this as the log likelihood or the log of the probability. It's going to serve the exact same purpose for our purposes. So now we have everything in a log scale. And what we want to do now is we want to take the derivative of this so that way we can solve for where the slope is equal to 0. And so we just dig back deep into our memories of the joys of calculus, and we remember things such as the chain rule, where you do everything on the inside first, and then you do the outside stuff, right? So the first step that we can take once we get to here is we can start dropping stuff down. So I'm going to say x times the log of p plus n minus x times the log of 1 minus p. That looks like the letter C. Let's make that look like a parentheses. Okay, so that'll be, oh, well, that's a problem. So that's where we are at this step. And now again, remembering the chain rule, now we do the stuff that's on the inside. So it's going to be x. If you remember take the derivative of log of something, once you go into derivative land, it just simply becomes the reciprocal of that value, plus n minus x, and I'll go ahead and I'll keep that in parentheses. And now over here we have log 1 minus p, so we have a number of things. First thing we do is, on the inside, we're going to take that negative p, and that's going to become a -1. And then we're going to do the remainder of the stuff that's in there, the log 1 minus p, which is going to be 1 over 1 minus p. Okay, so there's our next step. And then we just do a little bit of math, and what we should end up with is the derivative. So x times 1 over p is going to be x over p. Okay? And then we can take this -1 and just take care of all that stuff here. Okay, so it's going to be minus what? Minus n minus x over 1 minus p. And that right there tells us the change of the log likelihood as we change our parameter. So that right there is the derivative. Once we have the derivative, now we can simply solve for where, at what value at what value is the slope going to be equal to 0. And so I'll just go ahead and replace a 0 here. Actually, to save room, that's working real well. So I'll go ahead and I'm going to solve for 0. And now it's just a little bit of math playing around that we'll do. So let's say that it's going to be n minus x over n minus x over 1 minus p is going to equal x over p. And then we can do our cross multiplication. So we end up with Pn minus Px equals x minus xp, right? And go ahead and we can do, you know, the px's and the xp, it's the same thing, so they're going to cross themselves out. They're going to cancel each other out. So x equals Pn, we want to figure out what the maximum likelihood value is for p when the slope is equal to 0. So we just simply say p equals x over n. It's the number of successes divided by the total number of attempts. And that is the value for p. And so I know it's kind of convoluted, and as I promised, this is the only time we're going to do math, but the reason why I did this is that this is pretty basic calculus. This is, you know, first year of calculus type stuff. And I do this just to take away some of the kind of the black box, the mystery of, you know, why is the number of successes divided by the number of trials, why is that the maximum likelihood estimate for that parameter p? Well, the reason why it is because we simply took the derivative of it, solved for 0, and it turns out if you want to find out where that slope is equal to 0, the peak of that surface, all you need to do is take the number of successes divided by the number of trials. And so that's calculus. That's the extent of our math for the whole year. There's nothing really magical about maximum likelihood estimates. It's just simply if we understand what is the underlying function that's describing our distribution. So in this case, we had the probability mass function. All you have to do is just do the calculus on it and solve for 0. Now this is the only time this semester that we're ever going to do that. And this is a nice, easy piece of calculus to do. But when we start dealing with more complex distributions, like the normal distribution, you can do the exact same thing there, where you could take the probability density function of a normal, take the derivative, solve for 0, and lo and behold, the arithmetic mean will be the maximum likelihood estimate for that particular parameter. So, okay. That brings us to one last thing to kind of think about, which is just because it's the maximum likelihood estimate doesn't necessarily mean that it's right. It just means it's the probability of our data given some parameter. So the accuracy or the precision to which we're able to measure or estimate a parameter is going to very much depend on what our data actually are, which brings us to last thing to think about, which is called the law of large numbers. And so the law of large numbers is simply, it's a theorem that describes how precise you will be at coming up with the true value of a parameter based upon what your sample size is. And so there are certain situations, if we truly believe that the probability of getting heads is 0.5, for example, if you were to flip a coin, 3 times, you would never end up at that 0.5. You couldn't, because the number of trials would be 3. And so if you were to only flip a coin 3 times, you will end up with a maximum likelihood estimate for the probability of getting heads. But we know that that maximum likelihood estimate is probably going to be wrong because you're dividing by 3. There's no way that you could get to 0.5 if you only flipped a coin 3 times. And so this is what the law of large numbers is going after. Basically what the law of large numbers is telling us is that if we want to get a better estimate for the for the parameters that are describing the population that we're sampling data from, more information is always better. And so just to kind of show as a proof of concept with this, I set up a quick little simulation where our response variable is going to be y. And what am I going to do? I'm going to use a function now called rbinom, which will give me a random number drawn from a binomial distribution. And I'm going to have it work really hard. And I'm going to take, what is that? Is that 1 million? Yeah, it's 1 million. That's a lot. So I'm going to take 1 million times. I'm going to do one draw from a binomial with a parameter of 0.5. So basically what I'm doing here is I am simulating 1 million coin tosses. Okay? And so if I were to do that, just run that code. Here's all of my coin tosses. 1s are heads or successes, 0s are failures, and so on and so forth. I have successfully simulated a coin toss. One other thing that I'm going to do is I'm going to do what's called setting the seed, setting the random number seed. A lot of people that, unless you play a lot with computers, you might not realize that when computers are generating random numbers, it's actually pseudo-random numbers. They're not truly random numbers. The algorithm that the computer uses to generate random numbers usually sets the seed by whatever your clock says whenever you turn on the computer, and then it ends up doing it. The reason why we're going to set seed is that whenever we're simulating something, if we set the seed at 2, everybody will get the exact same answer. So for example, right now, if I were to just say rbinom, I'm going to take 10 draws, 0.5. So this is just doing 10 coin flips. Every time I do it, it's different. And every time you were to do it at home, it would be different. If I were to set the seed, and then I do it, and then if I were to set the seed again and do it, I will always get the same answer, which means that on your computer, if you set the seed at 2 and you took 10 and you ran this code right here, you would get the exact same answer as me. If we didn't set that, we would start getting divergent answers. Okay, so little coding caveat there. So I'm going to set the seed at 2, and then I'm going to do these 1 million draws, and then I'm going to go ahead and I'm going to calculate the maximum likelihood estimate for that p parameter. Okay, so there's my million coin tosses, and I'm going to pretend, let's say that I only flipped the coin 10 times. Okay. So again, the arithmetic mean also turns out to be the maximum likelihood estimate for the p parameter of a binomial. So if I were to do that, that is my maximum likelihood estimate for that coin toss. Okay. Now we only flip the coin 10 times, but based upon our data, that is the most likely value for the p parameter would be the probability of getting heads, say, being 0.6. So I can go and I can say, well, what happens if I had actually paid attention to the first 100 coin tosses? Okay, it's still wrong because, again, when we simulate data, one of the cool things about simulating data is that we are the omnipotent overlord of this computer universe that we're creating. We know that this is the right answer. 0.5 is the right answer because we simulated the data using 0.5. If we had only flipped the coin 100 times, our maximum likelihood estimate for the probability of getting heads is 0.45. You can say, okay, well, what if I did it 1,000 times? Getting closer to what we know the true answer is, but still, it's not exactly there. And say, well, okay, well, what about 10,000 coin tosses? You got me flipping a lot of coins, Jim. Now we're getting pretty darn close, right? But it's still not exactly 0.5. And if we were to just take all 1 million of those coin tosses, we're even closer. Again, 1 million coin tosses. We know the right answer is 0.5. That is the correct parameter for that simulated data, or those simulated data. But even with 1 million tosses, we're never really quite getting there. We're just coming up with a more and more precise estimate that's closer to the true population value, but we're never quite getting there. And that's what the law of large numbers is all about, is that kind of stuff. So okay, that was a lot of stuff, but hopefully we have a pretty good idea of how simple Bernoulli draws, when put together, create something that's called the binomial distribution. We've derived what the probability mass function is for the binomial distribution, so hopefully we have some appreciation as to where those numbers are coming from. And then we've also learned how to use those distributions, given a particular estimate for the parameter, to ask certain questions about what is the probability of observing this event versus what is the probability of observing some other event. So the binomial is appropriate when there's a fixed number of trials. You know, in our example, there was a fixed number of alfalfa patches that we could have potentially gone to. Or in the coin toss example, there was a set number of times that we flipped that coin. And it's appropriate unless the probability of the event is extremely, extremely, extremely low. There are other distributions that you can deal with for extremely rare events. I'm guessing that it probably won't be necessarily that important for the kind of data that you will be playing with over the course of your career. So, okay, and I'll say this a lot. The way to kind of get this stuff is you really just got to play with it. You got to play with R. Convince yourself that you understand how to answer, you know, different types of questions, and that you understand how these parameters are being estimated. So there we have it. Until next time, see you later.